Okay, next we are happy to have Professor Changzheng Li from Sun University who will talk about recent progress on gamma conjectures. Let's welcome.
First of all, I would like to thank the organizer for the invitation. It's my great honor to introduce my recent work. So here is for gamma conjectures proposed by Galkin, Golyshev and Iritani in around 2016. So, and actually there's another conjecture called conjecture O involved. And in my talk, I will mainly talk about conjecture O and gamma conjecture 1. And if time is enough, I will also simply, briefly discuss the gamma conjecture 2. And they say that, so we consider some flat connection of some brain connection, and this connection has two singularities. And on one singularity there is a so-called gamma integral structure, and on the other singularity there is some asymptotic behavior. So the gamma conjecture is the concern about the relation of these two structures somehow. So some of the highlight of the talk is to discuss the counterexample of the conjectures. Yeah. And this is based on my joint work with Sergey Galkin, Jianxun Hu, Hiroshi Iritani, Huazhong and Zhitong Shu. Yeah. I always like to start my talk from conjecture O just because this part is acceptable for almost everyone. And from here, if we consider the real algebra, and then any elements of the algebra will induce a linear operator simply by the multiplication. So we can ask what's the eigenvalue of the linear operator. Okay. For example, so we consider the case. So these three are three algebra. All of them are of dimension 2, and so we can fix the basis say 1 and x, and then we just choose the same element x, and then we can consider the linear operator. So because this is a basis, so we can write down the associated matrices. So respectively of the form these three. And by calculating the eigenvalues, it's quite easy to see that. So this one is 0, 0, this one is 1, minus 1, and this one is plus or minus the square root of minus 1. Okay, it's quite simple. But we can see that even if the matrices are very, very good in the sense that integers, still the root could be purely, could be complex number which are not real, like you can see here. And in this case, so here there is a notion of special radiance, that is the maximum of the absolute value of the eigenvalues. So from here we can see the special radiance here is 0, this is 1, and this is also 1. And here you can see that the 0 is eigenvalue, but it's not a simple eigenvalue. This is 1 is a simple eigenvalue, and this is even. 1 is not an eigenvalue. You can see some phenomena. Yeah. So that is purely algebra. But sometimes we can consider the algebra coming from geometry, or we may say topology. That is, if we consider a nice space. Then the cohomology ring automatically real algebra, and then we can do the addition and the multiplications. The multiplication of the cohomology classes could tell us some enumerative geometry information. For instance, if the two subvariety have the right dimensions, then the cohomology just equal to the number of intersection points of two variety times the point class. Then we can consider more geometric information. That is, we can consider information which do not count, not only count the intersection points of the varieties, but also the holomorphic spheres with fixed volumes, which pass through given subvarieties. So if we incorporate all this information together, then we we consider the here in this picture. That means we consider the small quantum cohomology. So from here you can see it is a deformation of the classical cohomology. In particular, you can see that if the value equal to 0, this becomes a point. So that means this information is contained in the quantum cohomology. Okay. Now we can state the conjecture O. And if X is a finite manifold, then we can consider the linear operator induced by quantum multiplications of the Chern class. That is for Chern class times beta, this is a quantum multiplication, and then specify Q at 1. So from here you can see that. So quantum cohomology, you can see it is a tensor of the classical cohomology of some polynomial. If we also specify OQ to be 1, that means it's a vector space, so they are the same. The only modification is the multiplication. Then from here, then C1 theta is a linear operator of finitely dimensional vector space. And then we can calculate the eigenvalues. Then they claim that the following should hold. First, the spatial radiance itself should be a simple eigenvalue. Secondly, so if we consider the eigenvalue of the same absolute value, then this should hold. In other words, all such eigenvalues should be in the root of unity. I mean, and here Ix is called the final index, is defined by the maximum integer such that this is again integral cohomology class. So from here, this is nothing but linear algebra if we forget the geometrical background. So that just means we study some kind of theory because from the quantum cohomology, so we can consider some linear operator. Also, so this is a typo. This is U. The typo. Just means we consider the eigenvalue consider maximum. Yeah. Okay. So that's why you can see. So everyone should be able to understand this. Yeah. And then we see one example like P1. Okay. So P1 is two-dimensional Z plus ZX, and so the final index is equal to 2. And as a factor, let me claim that the quantum cohomology, the quantum cohomology of P1 as an algebra is isomorphic to the polynomial ring moduli idea. So for conjecture O, we specify Q to 1. So this is just the CX module this idea. So this is the same example in the very beginning. And from here, we can see the spectral radiance, the eigenvalues are just 2 and minus 2. Spectral radiance is equal to 2, and this is 2. You can see that. So exactly, so they are the square root. Okay. Now, because all the three conjectures are stated for finite manifolds, and finite manifold is a complex manifold whose intercanonical length bundle is ample. So, from the viewpoint of the finite index, there are some partial classification. And the final index is always in between 1 and the dimension x plus 1. Here, all the dimensions are all the complex dimensions. And so, if this is equal to dimension x plus 1, then it is isomorphic to projective space. And if it is one less, then it is isomorphic to the quadratic hypersurface, the smooth quadratic hypersurface in projective space. And if one less again, then it is called the trapezoidal manifold. And here is some kind of manifold called Mukai manifold. Okay. For the smaller finite index, that is known. And for low-dimensional found manifolds, there are also some classifications. One-dimensional case, there is only one upper isomorphism, that is a projective line. And for dimension equal to 2, so it's simply isomorphic to like P1 cos P1, P2, or the piezo surfaces, that is the blob P2 at R points in general position, and here is from 1 to 8. If it blob up to 9 points or more, then it is not found anymore. So in this case. And in dimension 3, there is also complete classification. So there are 105 family classified by these mathematicians. I mean, just each of them give some study partial case. And then conjecture O was studied by Cheng and myself for the flag manifold G over P. Typical example including the complex Grassmannians. And also for some other cases, there are three types of the examples. The first one is the more, in my opinion, is the most important one in the sense that flag manifolds, so there are some positivity. So that the linear operator is essentially a non-negative matrix. And then long time ago in 19,000, I mean, Perlin and Frobenius, they studied positive matrices and non-negative irreducible matrices, and there is a PF theory. And you can, if you know that, then you can see that the statement of conjecture O is very, very close to the PF theorem. So in that sense, this is quite close to the PF theorem. And this class is like found in a complete intersection in Pn. So in Gromov theory, so there is called a quantum Lefschetz principle. Means that for some information, if you know it for ambient space, then you also know it for the hypersurface of this ambient space, something like that. But it's not known whether this is true for conjecture O. In other words, if we know the conjecture O holds for the ambient space, we don't know whether it holds for the hypersurface. So we can ask this kind of question. And the last class is like the blob. If we know the base is true, whether it is true for the blob, so we may ask this kind of questions. Somehow, conjecture O is very elementary. But also because of this, I think it's very difficult just because there is no tool to study the eigenvalues in general. Even we learned it very, very early. Okay, now let me explain a little bit about the name and also what we want to say about these conjectures. So for mere symmetry, so it is some equivalence between information from different sides. Roughly speaking, we always say A equal to B, and the A side we say information from simple geometry, and the B side equals information from complex geometry. And so there are many mirror symmetric statements for different objects and at a different level. In our case, on the A side, we consider found manifold. Then the B side is called the lambda-Kitzbühel model, which is a pair of mirror space X check. It is a non-compact Kahler manifold together with a holomorphic function on this space. Then it is expected in mirror symmetry that if they are mirror to each other, then as an algebra, the small quantum cohomology should be isomorphic to the Jacobi ring of the superpotential F. And the higher level is that on both sides they have Frobenius manifold structure. Then as a Frobenius manifold, they should be isomorphic to each other. And starting in the middle, it says that the eigenvalues of the first class should show the one-to-one correspondence with the critical value of f, and this correspondence is really equal. Okay. Okay. Then in this sense, then on the from the viewpoint of homological symmetry, so the superpotential here we can consider when it's a cycle associated to the critical points. And then somehow we say that so the derived category that is on the B side of X should be equivalent to the Fukaya side category of the superpotential F. And then that is some objects in the derived category of X correspond to the critical points of F, or equivalently the critical value of F. So as a philosophy, we may say that. So a spatial object in the derived category may or should correspond to a spatial eigenvalue of the first class, or in other words, a spatial critical value of superpotential somehow. So in this philosophy, then they say that so the structure shape of X should correspond to the spatial radius T. So somehow that's the name of. And the gamma conjecture too are in this sense. So with one more assumption that the quantum cohomology to be semi-simple, then each the exceptional object of one-to-one corresponding with this simple eigenvalue, roughly. Okay. So far, any questions? Now we are going to explain gamma conjecture. Just because that part will be more technical, so I just try to stop here and ask a question, because now everything is easy and okay. Okay, so to formulate the gamma conjecture 1 and gamma conjecture 2, so we need to say a bit more about the Golomythan invariance. So on the morning, we mainly also talk about Golomythan invariance, and here I try to not to define this technically. I just say something. Okay. First, we consider the multispace of stable maps. That is, we consider, you may consider, roughly speaking, you can say it is a quantification of holomorphic map from P1 to touch space X, and these marking points, and some condition, and equivalence relation, and the length multiplication. So you can say the essential elements is like this. Okay. G is genus. G equal to sorry. In general, this should be a curve of genus G. I'm sorry. This should be 0 because quantum cohomology just gamma conjecture only consider the case of G equal to 0. So, okay. Yeah. So this 0. Okay. And evaluation map is simply just as evaluation map just here element just map to the ith the value of f at the ith point. And the Li is universal cotangent line bundle at a pointer is just the cotangent bundle of the curve C at the pi. Okay. Then you can see that this is the GW invariant. So that is, you can see the first class of the line bundle and the cohomology class pull back from the cohomology class of X. So in other words, you can see that. So this type of invariance is a part of the intersection theory of the model space. Okay, you can see that. That's all. So this is a formal data. Okay, that is we choose a homogeneous basis, and then we can define a potential by incorporating all necessary invariance, and this is formal power theory, and it is analytic at origin as assumption. Okay. Then, and this Poincare pairing, then the big quantum cohomology is defined by in this way. And small quantum cohomology, you can see that the big quantum just means you consider everything in the total space of the cohomology. Small just means you will restrict to H2 still. So still, it is the classical Kaplan contributions from curves in X. And it's impressive, we just need to know. So the quantum cohomology is associative with identity, and it is commutative just because for simplicity we assume all the cohomology has even part, there is no odd part. Okay, for simplicity. Otherwise, it's graded commutative. So then we can consider a meromorphic flat connection called the Dubrun connection on the trivial vector bundle of the base. So the fiber is the cohomology. The base is the cohomology times P1. Here B is the simply connected omnipotent zero, such that this is absolutely convergent. And you can see some form. So the connection along the t direction is defined in this way, and the quantum product is involved here. And on the z direction, the Euler vector field is involved here, and the Euler vector field is of this form. In particular, if we restrict to H2, you can see that so this topology degree. So that means for the Ti topology degree in H2, this is 2, so this is 0. In other words, E becomes fourth class if we restrict to H2. So you can see that Z direction, this is fourth class in H2. And the mu is some degree operator. Now, the Dubrun connection has two singularities. In the infinity, so it is a regular singular, and at z equal to 0 is irregular singularity. And the gamma integral structure, which we will introduce very soon, is information around the regular singularity. And on the other side, AEFS is around z equal to 0. And here we can consider the global flat section on B, global flat section, so B is somehow here. This technically we consider the universal C star hat is the universal covering of the C star. And so this universal covering map to C star, and from later we can consider the pullback connection of the bundle over here. This is just the notation. Okay, then we will see. And then we can consider the cohomological framing. This is isomorphism of vector space. In map a class to a flat section. And here L is some tau parameterized the former linear endomorphism introduced by Iritani. He followed a similar operator by Giventhal, and so consider likely. And once we fix the alpha and the value z, then it is analytic near infinity, and then we can do the analytic continuation to the universal covering. So here you can see this is a isomorphism of vector space. And then this is a linear map. So this is X is the Golyshev group of the topology K theory, so of the complex vector bundles. In particular, this is a abelian group. And this is a vector space. So this defines a linear map, the Z module from the K theory to the space SB. And the CH here is modified, some characters modified in the sense, so some coefficient lays some twist by coefficient. And the gamma class now, the title is gamma conjecture, so everything should be related with gamma. And the gamma just means gamma function, the same in the first year undergraduate, gamma function. And using the gamma function together with the chain roots of the cotangent band of the tangent band of X, then we can define a class. You can see that this is a symmetric function in xi. Then we can do the Taylor expansion, and then it is because this is a cohomology class, so it's just a finite term. You can see that this is really a cohomology class of X, and it's called a gamma class. And this class appeared in mirror symmetry a bit earlier. Even started earlier in this year. So Huazhong claim Tyson Yao they study some hypersurface Calabi hypersurfaces, and they obtained they proved some remarkable identities, and in 2000 around 2000, so this mathematicians found that. So okay, everything actually can be interpreted by the inverse of gamma class. That is 1 over this gamma class. Yeah. So and now we see the definition of gamma integral structure. Just very simple, just the image. So the global one, just the image. The image of the JBK. So that is so this is a linear map. The image. So this is a vector space. The image is apparently, so you can say it is a abelian group. So this is a abelian G, abelian finite dimensional abelian group. Inside the SP. And also, just means SP you can see a global family in tau, but you consider fiber rough speaking the S tau. So the gamma structure in S tau is just like this. Okay. So this is for lattice, for rank lattice in this space somehow. You lattice discrete. The lattice is discrete, so in the vector space. Okay. Okay. Now, okay, so there are some related work, and so Iritani introduced the gamma integral structure. Because we will not talk much about the mirror symmetric gamma conjecture, let me just make a definition at this moment, even before gamma conjecture. Okay. So somehow we say the mirror symmetry A side is final, B side there is superpotential F. And from the B side, there is also some natural integral structure by using the superpotential, by using the oscillating integration over the left symbols. And on the A side, so there is gamma integral structure defined by Iritani in this way. And he proved that for totally final manifold, the structures on both sides match with each other. And now this is referred to as mirror symmetric gamma conjecture. If we that means if you consider other final manifolds, then the A side, gamma integral structure should match with the B side, even though I didn't talk about the B side structure yet. So anyway. So the object is something like so superpotential like Z. F is superpotential, this is the volume form. So there's a gamma. So for instance, for gamma conjecture 1, so we will come to here again. So let me see here. Now let us say gamma conjecture 1 first. So if we restrict to the real positive real line, okay, and consider this vector space, that is just flat along the z direction and has the moderate growth. That is, it is of the form by polynomial order for some n. So we consider this kind of space. Then if conjecture all holds, then this is one-dimensional. This is one-dimensional, then gamma conjecture 1 just says that. So if conjecture all holds, then this one-dimensional subspace is generated by gamma section of all x in the sense that. So this is so this one-dimensional space is generalized. It's generated by this class. So now you see that. So this is vector space, and this is one-dimensional in a vector space, but this is just the lattice, and this object. So let is this spatial one-dimensional vector subspace happen to pass through a point in the integral gamma hat integral structure. So in this way. Okay, now we can see that. Which one? So everything here is for final, but historically it's like that. So this kind of notion is also called central charge. Appeared for Calabi-Yau first. I mean, it's defined by orthogonal appeared for Calabi-Yau first, and then Leslie then proposed gamma conjectures for finite manifolds at that time. Yeah, so, and then after that, also Iritani like Abzai folk also. I mean, they study for come back to Calabi-Yau and learn later Calabi-Yau version of gamma conjectures. And for later version of gamma conjectures is more like mirror symmetric gamma conjectures. We can state that in this sense. Here, just here. So this is the A side, this is the B side. Yeah, in this sense. So yeah, okay. Okay. At this moment, this is set for A side only, but mirror symmetric is just A, B. Okay. And this is another equivalent formulation in terms of J function. That is, okay, this is one dimensional. We may say up scalar is just defined given by one class. Okay. And if conjecture all holds, LAM3 also proved that. So the J function, okay, you can be defined by using this GW invariant. And you can see that this is a formal paralysis in 1 over Z. In other words, this is so near to the infinity. Okay. Okay. But you can consider if this holds, the first one could be treated as a definition, and the second equality is a proposition. So if a conjecture all holds, then at Z equal to 0, there is a asymptotic, this is a constant, up to a constant. So there is a asymptotic expansion of this form. The leading class is some commutative class, and the height is Z power this sort of things. And then in this way, then gamma conjecture 1 says that the leading term of the J function in this expansion is equal to gamma class. So yeah, if you here if you normalize it such that the class is of the form 1 plus a higher degree, so this is equal. Otherwise, it's up to a scalar. Okay. Now, gamma conjecture was proved for less cases. So the first one is complex Grassmannian. At the same time, when they proposed this conjecture in the Duke-Mason paper. And also for Founder threefold of Picard-Lincoln 1, it was studied by Golyshev and Zagir. And Jianxun Hu, Huazhong, myself, and Paul Yan proved the case of final final surfaces. The basic surface is a two-dimensional final manifolds. And then can show it for final computer insertion in projective space. So this is for hypersurface, this is for final index larger than 1. This for all cases, in particular for final index equal to 1. And for totally final manifold, if they satisfy two conditions. One condition is just like about the conjecture O. The other condition is called the conical condition. If we assume the two, then Galkin Iritani prove that any totally final satisfy the two conditions will satisfy gamma conjecture 1. And these conditions was verified for the graph of P along PR by Zhitong Yang. So basically, so it's difficult to compute what we need. So I think for most of the class, except beyond the graph meaning cases for many other cases, not for other cases. So basically, we have to apply the quantum lattice principle. That is, if we consider a hypersurface, generalizedly, we can consider the final computer insertion. If the empty space is X and Y is inside it, and if the gamma conjecture 1 holds for X, and if conjecture O holds for Y, then the gamma conjecture holds for Y. So this is true in general. The reason is that by using quantum lattice principle, if the J function of X has some kind of expansion, then the J function of Y would also have similar of the same form of asymptotic expansion. So together with the conjecture O, then the true. Yeah. Okay. So far, any question? So these are for. Then we will come to our recent work. Okay. Somehow, especially if you roughly remember the page of what is known for conjecture, or you can see it's a full page. So it seems that many cases were verified, and then so we expect that it holds, but it turned out that it's not true for this simple example already. So this is a P1 bundle of a Pn. This is a polyfinal manifold. So if we consider n equal to odd and larger than or equal to 3, then it doesn't satisfy conjecture O. And the strategy is that, so on the A side is always difficult. The quantum cosmology is difficult to study, and the eigenvalue is difficult. Yeah, somehow this sort of things. But for mere symmetry, we expect that the eigenvalue of the first class coincide with the critical value of the superpotential. This was just proved for toric final manifold, and also recently for flag manifold of type A by myself and some of my collaborators. And in the toric case, it was known to many experts, but it was first proved by Alux in his paper. Okay. So from here, then we can just study the critical value of the superpotential. We will see one example, this example precisely, and then we reduce it to the analysis. So this kind is very elementary analysis of the just analysis of the critical value. Okay. So in this case, even though the conjecture does not hold, we can make a variant of gamma conjecture such that the statement still holds. And also, about 2 months ago, yeah, so this person posted a paper on archive a few months ago. Okay, yeah. So they studied non-Kahler monotone symplectic manifold. Some example. In that example, the spectral radiance is an eigenvalue, but it's not simple. Even so, he can study the coefficient of the J function such that this limit of the coefficient still holds in in some sense is some kind of equivalent. Yeah. It just says that. So the statement of the gamma conjecture 1 could hold in some more general cases somehow. The second?
Like what why this fault?
Oh, later we will say. Later. Yeah, we will see for all cases. So for most of the story, we just care about the first part, first part. Yeah. And even to formulate the gamma conjecture 1, we just need the first part. Okay. We will come back to the example again. So we will just say a bit more first. So we can relate the assumption to state a variant of gamma conjecture 1. So original assumption is that we assume the fundamental manifold satisfy conjecture O. But now that means the spectral radiance should be simple eigenvalue. But now we do not need this. We just say that if it has a simple rightmost eigenvalue, that is, so the eigenvalue is a complex number. So this is C, this is real, this is. So if it has the complete points here, and the other point is like here, that is the real part is the maximum one. It's a simple eigenvalue. So simple rightmost in this sense. Okay. Yeah. Then conjecture holds, then of course it has a simple rightmost because the spectral length is absolute value, right? Yeah. But the converse is not true. One thing is that still we can consider the subspace. And now we just consider here moderate rate growth is not a T, not a spectral radiance, but the maximum of the real part of the eigenvalue. So this is also one-dimensional as long as this operator has a simple rightmost eigenvalue. So once this, then we can still just state that okay, this one-dimensional subspace is given by the structure shift. So in this way, we call it variant. So it has the same spirit of the original gamma conjecture. Okay. Then, if n larger than or equal to 3, if n is odd, then the conjecture O does not hold. But we can consider the variant of conjecture 1, then it holds. And if n is even, then it satisfies conjecture O. But things becomes even worse in the sense. So for even case, even the variant, so the gamma conjecture 1 does not hold. Okay. The question is that For uneven, conjecture or hot just means so X is again one-dimensional. But the gamma conjecture does not hold. That means it's given by some class, but this class is not coming from the gamma class. The next question is what it is. Yeah, okay. Okay. So, so this is some strategy we can just skip it first. And we need to emphasize one thing. So in the statement of conjecture O and the gamma conjecture 1, everything was stated by specifying Q equal to 1 first. That is tau equal to 0. Okay. Just like if you remember the operator alpha is mapped to was the alpha and Q equal to 1. That means so. And second thing is that because of this counterexample, then we want to study what happens for the case of n is even. Yeah, what's the unexpected class? Then we verify Q. Yeah. Verifying Q, it turns out that if we verify Q, this would reflect the birational geometry of X. So in our example, so this is P1 bundle over P1. It is a totally fundamental manifold, and indeed, it's there are two morphisms. One way is natural one, so this is P1 bundle. So another one is that you can see that it's some kind of graph of the weighted projective space, so n copy 1 of n. Yeah. And this is geometry. You can see the morphism. And for Miller symmetry, for totally final, there is a canonical way to write down the superpotential. In this case, it is a holomorphic function C star the dimension n plus 1 to C, and just simply defined this x1 to xn and y2, so this n plus 1 variables, so defined in this way. And we say that, so Q2 equals 0, so Q small will be related with phi. Q1 small somehow related with this one, somehow. Related somehow you can see in this way. So this Q corresponds to some extreme array. And for the extreme array, it's contracted. So from one way, you get this morphism, the other one, you get this morphism. The other one is a fabulous. Okay. Now we see, for example, for x4, n equal to 4. For n equal to 4, the Q are real, positive real, and so here is if Q2 over Q1 square is small, then the critical value of superpotential, that is the eigenvalue of the first class, are of this form. And so the special radius is T minus. T plus is called the conical point. That is f. You see this is a function. Then this function could restrict to a positive n plus 1. Okay? If we restricted this function to the positive part, so this is the real smooth function, and it has a unique global minimum So this is a conical point. And the t plus is f of this point. Yes, because 1/3 of the PPT will be above the gamma conjecture 2 and will be skipped. Okay. Okay. So, so from here you can see. So this is a conical point, the critical value of a conical point, and this is special radius. And when Q2 over Q1 square become large, then the conical point becomes the largest one, and this value becomes smaller one. And the number already denote the same critical value. Just see the behavior when we value Q. Yeah, you see the picture like this for X4. And for order, for X5, you see that. So this is always the smaller one. This is always the smaller one. Smaller in the sense, so it's a real number smaller. But actual value will become larger. Yeah, that's why for this case still, yeah, right. Okay. Yeah. Then, as a theorem, so we can show that. So if Q near to the pi 1 boundary, pi 1 fibrotic boundary, then this class is actually given by the tau head, gamma class. But for the other one is given by this class. In particular, this is the answer to the previous question. That is, so for xn with n even, the special radius does not correspond to the gamma class. It corresponds to this class. This class coming from this object somehow. Yeah. Okay. Then we can ask some questions arising from these counterexamples. The first one also, so this theorem also partially answer these questions in this example. That is, in the very beginning, we just consider Q equal to 1. Yeah. The conjecture of set light or special radius that. But in general, we can ask, so we value Q, we can ask if there exists a point Q, not necessarily the special pointer at 1. Okay. So can we find some Q such that the corresponding class such that, okay, the eigenvalue has a simple rightmost eigenvalue. Yeah, okay, contains this one. And the corresponding one is given by the gamma class. So this is one question. And also can we find it in the real coefficient? This is could be complex, but real. And could we describe the region where it holds? Okay. Now we see some data. So for Tolly funnel, there's a web page which gives us information of the Tolly data of the Tolly manifold, the Tolly funnel manifold of the dimension less than 7. So from that data, so once we know the generators of the one-dimensional ray of the fine structure of the Tolly funnel, then we can write down the superpotential. And then we can verify it in the case of Q equal to 1 for the original conjecture O. Then we see that for here we just verify the first part. For totally final manifold up to dimension 3, everything holds. For dimension up to 4, so space radius already no longer could become false. But it always has a simple rightmost eigenvalue. Property OP just means we add one more condition. We need to assume simple right eigenvalue and also conifold point condition. And here we can see more and more. So the bad thing is that, so you can see there are many examples for which conjecture O or the weaker condition does not hold. A good thing is that there are not so many in the sense, so about 10% or even less. Yeah. So here you can see, so about 5%. Yeah. So you can still expect that generically this could hold. So how could we characterize this toric funnel, whether it holds or not? This kind of question. We just noticed a counterexample. It's far from to get anything further. Yeah. Yeah. And also because we just verify this numerically, so we don't know what's the what's the character of these counterexamples. Yeah. Then here is some diagram that is, I can say here. So originally we assume conjecture O, then the gamma conjecture. Well, this is the original conjecture, so this is Q equals 1. Okay. Now we say, okay, this is just actually essentially 1. Okay, then we say that, okay, so this is a sufficient condition and this is not enough because of the counterexample. Then we should modify it to be 1 and 2. This is a conifold condition. Roughly speaking, T is equal to T plus. Roughly, okay? So, need 2. Then the problem is that on A side, the first one is replaced by simple rightmost, the weaker one. The OAA. So this is just replied by simple rightmost. Okay. So for toric final manifold, the B side, this condition is precise. Just means so there is a canonical superpotential, and it is proved that for the toric final always there is a unique global minimum which is called conifold point, and then the special radiance should coincide with this. The preimage only one this point. Yeah, the conifold point. But on the A side, it's difficult to formulate this just because for general final manifold, there is no canonical way to construct the superpotential. Yeah. Even for the existence, still there's some question. Yeah. Somehow. So we just expect that. So the correct sufficient condition should contain two parts. Yeah. First part is eigenvalue. The second part is conifold point that they coincide with each other. Yeah. Okay. I think time is out. Then just show one page and then we stop. And so for gamma conjecture 2, is the assumption is that the big quantum homology should be semi-simple. So once this is semi-simple, then just one page. Okay. So the following conjecture that the big quantum homology originally conjecture that the small quantum homology is semi-simple if only if there exists a full exact collection. By then later counterexample because of that, then this should be modified as big quantum homology. Okay. The latest assume the big quantum homology is semi-simple. Then you can see there is a full exact collection. Then gamma conjecture say is that though. Here. Okay. Then this should correspond to this should correspond to here. And the precise I you can see is some class just like correct pointer or eigenvalue just correspond to one class, and this gives this some kind of correspondence in this way. You see this is statement. And it's proved just for very few cases. For Grassmannians, the same time like them. And the total fundamental for recently proved by Bo Hanfang and Peng Zhou, and his surface faculty, and also Jianxun Hu and Huazhong they proved this case for smooth quadratic hypersurfaces. Then I'm done. Okay.
Maybe not related question here, but like for the first homological mirror symmetry conjecture related to the first gamma conjecture, we state like there is some vanishing cycle corresponding to the structure shift in the other side. So I'm curious here in the complete intersecting Calabi-Yau in Grassmannian, like Coffee and Grassmannian, we has more vanishing cycles here. Do we have corresponding generalization?
I mean, and so in that sense, I think if you consider all other vanishing cycles, right, that is gamma conjecture 2. Somehow. Gamma conjecture 2.
It's simplicity, right?
I mean, somehow you can say roughly think that. So it just means so each critical point has a vanishing cycle. And this vanishing cycle corresponds to one object. So this correspondence is just gamma conjecture 2. But in that case, they just say globally. So the whole thing corresponds to this. There's one correspondence. But the gamma conjecture 1 just says one spatial point. The difference.
The primary, I'd say, the primary discriminant.
Yeah.
Of OX.
Yeah.
I see.
Yeah.
Okay, thank you.
I think Abdul Kanash Sheridan has a paper that relates gamma conjecture to SYZ conjecture. And
Abzaid, Iritani, and Gong. I mean, the paper has 4 authors. That paper. So that is just this kind of that paper is about this kind of things. And some central charge equal to something. That is for Calabi-Yau work.
Any more questions? I have questions. So, do we know anything about QB44? What is the relation to the proposed proof of non-rationality of generic QB44 by conservation?
Yeah, at least in second part, so we also add some remark. But somehow that proof somehow a very important work was given by Iritani, the quantum the quantum homology of block. Okay, so consider the decomposition of the module around the Q near to 0. Yeah. So we add some remark, but it's hard to say. Yeah, hard to answer this question. Sorry.
Yeah, thank you.
Yeah.
So, If no more questions, let's thank speaker.
Oh, sorry, just one thing. Little bit. So the result. So from here, this is PNO plus ON. So from here to from here somehow, I mean the idea is like that. So the derived category here. So this is somehow is some kind of graph. And so let's first embed into this one. And the right orthogonal of the complement of this subcategory is a one-dimensional subcategory. And so it's given by some object, and this object is just there. In that sense, so some relation between graph. Yeah. Let me see. For hygienists, I think, let me see. Yeah, I have no idea. Yeah. But,
Okay, let's thank Professor Changzheng Li again for the interesting talk.